Okay, so yesterday when you guys were in the algebraic proofs, we start there because sometimes in algebra it's easier to do things, and then we're trying to explain how that relates to these more complex geometry ideas. Okay, so we started out with algebra because those tend to be the easier proofs. You've solved equations probably over 100 times by now. And you know kind of the process of I got to do this first, and then I do this second, and then I do this third, and then I get my answer. Okay, or whatever that might look like for your problem. But now, how do we take this idea? How do we take the solving an equation idea and justifying my reasons and apply it to geometry? How do I start taking this now and extending on it a little bit more into what we're talking about today? So, like we did yesterday, you're going to see two column proofs where you have statements and reasons. Nothing really changes as far as how they're set up. You're always going to begin with your given information, and then you're trying to connect the things that are inside of your problem in order to make these relationships. Now, before we get too far into this, there's a couple things I want to talk about. I want you at the very top of your page, I want you guys to write down this, which is, it's called the definition of congruence. This is a property that didn't probably show up yesterday in the chart with the algebraic proofs because this only really happens in geometry. But what definition of congruence says is that you can switch a congruent for an equal sign or vice versa. So I'm kind of drawing like an arrow in between them to try to symbolize you guys could have a congruent sign and switch that for an equal sign, or you could have an equal sign and switch it back to a congruent sign. We can do that at any point within our proofs if we feel like it's going to be helpful for us. Here's why we have that property. This is when you would need to use it. Way back at the beginning of the year, when we were in that very first unit, we were doing all the constructions with compasses and stuff. When we went through our vocab sheet, we had the word on there on our vocab sheet, congruent. And then on the next page, we had the word equal. And we talked about like correct notation for when you needed an equal sign versus you need a congruent sign. Okay. So if you don't remember, I'm going to write some stuff up here on the board. If you had something that looked like AB with its hat on, and it was congruent to CD with the hat, you see how they all had the hats, right? So that was correct notation. If we had an equal sign, they shouldn't have hats anymore. Okay, that was kind of when we talked about, like, when do we know, should we use a congruent sign versus an equal sign? It kind of depends on what's the context of the problem. Are we just talking about that these two things look like they're the same? Or are we talking about actual numbers and actual measurements here? Same thing happened with angles. If we just had angle A, we would say that's congruent to angle B. But if we had a little m in front of it, do you guys remember what that m stands for? Measure. Then it switched to an equal sign. Okay? So I think when we talked about that in class, I gave the example of my desks in here. These tables. Do you guys think that these two tables, or all the tables in here, look the same? How do we prove, though, that they're the same?
Measure them.
We have to start measuring them. We have to figure out how wide is it? How long is the top? How thick is this top part? How long are the legs? And then we would be able to compare from this desk to that one to that one, all of them in the room. I should be able to measure all of them and see, are they actually the same or not? But when you start working with actual numbers, that's when you have an equal sign. When I'm just thinking about the idea of like these look the same, that's talking more about congruent, okay? So in geometry, especially in proofs, there's going to be times where you maybe start out with a congruent sign, but you need it to switch to an equal sign. Or you have an equal sign and you need to switch it back to a congruent sign. So that's when you're going to see this definition of congruence pop up. And it just says, like, you have the ability to go back and forth between those two symbols, depending on maybe if you're working with actual numbers or if you're just talking about this idea. The other thing I want to kind of go over again with you guys is the transitive property. You talked about this yesterday, but the transitive property shows up a lot in geometry proofs. And so I want to really make sure you guys understand how the transitive property works. Okay. Okay, so yesterday you would have said that like if A equals B and B equals C, then does anyone remember what you would have written? A equals C. Okay, so let's illustrate this. And maybe this was talked about yesterday, but when you illustrate this, I want you to think about, I'm going to pick on a couple people in here, okay? Raise your hand if you have a dog. Okay, I'm going to pick on you three because you're closest to me. All right, if Keegan has a dog, okay, we know he has a dog here, and we know that Morgan has a dog, and we know that Maddox has a dog. Okay, so all these three people here have a dog at home. If I can say then, all right, because you have a dog and you have a dog, you're the same. Because you have a dog and you have a dog, you're the same. What can we conclude about Keegan and Maddox? They're the same because they also have dogs. Okay, that's how the transitive property kind of works. Is if I can show that like these two quantities are the same, and these two quantities are the same here, I can, sorry Morgan, skip over you, and I can connect these two people together. And that's what transitive is going to be doing in our geometry proofs as well. If we start to see a piece in the middle that's the same, we can kind of skip over that or cut that piece out of the problem and go straight from the first quantity to the last quantity. And that's kind of what that transitive property talked about yesterday. But sometimes when we think about it in like number sense or letter sense, it can be a little bit confusing. So maybe going forward now, if I start talking about like dogs, you guys will start to recognize, oh, she's talking about the transitive property again. Okay, so let's get into a couple of proofs here. The first couple that we're going to talk about are just proving theorems. Theorems are like rules or general ideas that have been proven over and over and over again in the geometry world, and they always work. So we're going to do these first two because they show up a lot inside of our geometry proofs. And so when I have these being used as reasons, I don't want to have to go back and like reprove it over and over and over again. So if we prove it one time together, then you can continue to use it forever. Yeah. So the two we're going to talk about is the transitive property, which we just kind of illustrated a little bit together. And then we're also going to talk about vertical angles. Okay? All right, so let's start with this first one. We're going to talk about the transitive property here. So in my given information, they're telling me that angle 1 is congruent to 2, and that angle 2 is congruent to 3. They've already got that written down here in my statements, so my first reason should be given. Again, we should already all know that based on what we talked about yesterday. No matter how much or how little you know about proofs by the end of this unit, you guys should always be able to start it because it's always the given to begin. Okay, so you should always be able to write that down. Now, if you look at step 2, what changed from step 1 to step 2? What's different? Yeah, there's a little M for measure. There's an equal sign now instead of a congruent sign. So I had that up on the board a little bit ago. That's flopping from congruent to equal, and that's using that property we wrote at the top of our page. We're going from congruent signs to equal signs. So that reason there is definition of congruence. And I'm going to abbreviate that. You guys feel free to do the same thing. Okay, again, the reason why we want to do that is because it's easier to work with actual numbers to be able to show that these things are the same. All right, so I'm just going to throw these numbers up here. I don't actually know how much these are. I'm just giving you guys some context here. Let's say we know all three angles are 110 degrees. So looking at number 2, they're saying that the measure of angle 1 is equal to measure of angle 2. Measure of angle 2 is equal to measure of angle 3. They're all 110 degrees. What do both of those statements have in common? So what does this half have in common with this half? What? They're the same as the measure of angle 2. Okay, this is back to the dogs here. What can we do if we want to skip over the person in the middle? We just cancel them out because we know that the first 2 pairings are the same and the second 2 pairings are the same. They both have 2 in common, so we can skip over angle 2 and say that angle 1 and angle 3 are congruent to each other. That's using the transitive property. And then we're going to go back to congruence because we had an equal sign on step 3. We're going back to a congruent sign now on step 4. So that's using that definition of congruence again. Like I said, transitive is going to show up a lot in our geometry proofs, especially when we're trying to make connections between angles to each other. And so now that we kind of know how that works, we don't have to keep proving it over and over and over again. We can now just use the transitive property. Okay, I'm going to do the same thing now for my vertical angles. So the second one is giving me the fact that angle 1 and 3 are vertical to each other. I want to be able to prove that angle 1 and 3 are congruent. Now, we kind of already know that because we've talked about vertical angles already in this class. We know what they look like. We know that their measures should be the same, but I want to be able to prove why. Why does that always happen? That way I don't have to keep proving my point on that when I'm trying to use vertical angles inside of other proofs. So 1 and 3 are vertical to each other. That's your given information. So go ahead and write down reason number 1 is given. Okay, because we know that. All right, so let's see what they wrote down for step number 2. It says that the measure of angle 1 plus the measure of angle 2 is 180 degrees. Do you guys all see where 1 and 2 are at in your picture? Okay, so they're saying that those two are 180. And then they also say that 2 and 3 also add up to 180. What kind of angle pair are we working with there?
Linear pairs.
Linear pairs. Because they're side by side, they're adjacent, and they're adding up to 180, which is that supplementary idea. So we know that those are linear pairs. Because 1 and 2 are a linear pair, 3 and 4 are a linear pair. So I'm going to go ahead and write that down for number 2, linear pair. Really, I could have done that with any of those pairings. Like I could have used 1 and 4, 4 and 3, if I wanted to make a connection that way instead. I'm just trying to somehow get 1 to 3 together without just saying, well, they're vertical. Because you can't really use the reason you're trying to prove as a justification for what you're saying. Okay, so what happened from 2 to 3? What changed? What's different from step 2 to step 3? Keegan?
Not saying what they equal.
They don't have the 180s anymore, right?
They're saying they're equal to each other.
They're saying that they're equal to each other. So we've kind of we saw that they both had the 180 in common. And we're skipping over the 180 right now to say that the 1 plus 2 is equal to 2 plus 3. What property is that?
Transitive.
Transitive. Okay, you could say transitive here. Some people argue that it's substitution because we know that they're both equal to 180, so we're substituting a new expression in. You could really argue both ways there. So I'm going to put on number 3, transitive / substitution, because really I would take either one as a reason there. Then what did they do? How'd they go from 3 to 4? They got rid of the 2. How do we just get rid of it?
Skip it.
How though? Transitive could happen again. Is there an operation we could have done to get rid of 2? You could have subtracted it from both sides. There is an equal sign in between them. So if you think about this like algebraically, like from yesterday, I could have said, well, I'm going to subtract the measure of angle 2, and I'm going to subtract the measure of angle 2 on this side as well. And when that happens, they both just cancel off and go away. So again, you could kind of argue both ways. We could use transitive again because we notice that they have that common quantity, so we're able to skip it over, or you could have used subtraction. So I'll do the same thing here. Either one you could really argue is happening. And then what happened from 4 to 5? What's the only thing that changed? The congruent sign popped up. They got rid of the M's. What did we say that reason is? Definition of congruency. Okay, now if you take a look at these two problems, guys, they both end in that definition of congruence. Okay, that's not always going to happen. So I don't want you to think like, oh, every single proof I ever do is going to end this way. It doesn't always end that way. It just happens in this case because we had to get back to our congruent signs. Sometimes you won't be leaving the congruent sign at all, and you won't have that property show up. So I just want to point that out because I don't want you to have a misconception of you always start this way and you always end this way on those proofs. That's not going to happen every single time. But now that we've proven those two things, we can now start using transitive and the vertical angles theorem for any proofs that we see going forward. And so we're going to get in now to writing like entire proofs. Like those ones were kind of nice because they already had the statements written out for us. But sometimes you have to start from scratch. So if you guys look at the one on the bottom here, we're going to start out by looking at some proofs based off of those angle relationships that you've already learned about. We already know what vertical angles look like. We know what corresponding angles look like. We know what alternate interior, same side exterior, blah, blah, blah. We know what all those angle pairs look like because we've talked about them. So we're going to start with proving things with those angle pairs for today. Now, when you guys do this, okay, when they want you to prove that a certain pair of angles are congruent or supplementary, you are not allowed to use the angle pair that you see as your reason. So, for example, on this first one, it says, given parallel lines, prove that alternate interior angles are congruent. They want you to prove up there, it says 3 is congruent to 6. Do you guys all see that? 3 is congruent to 6. Look at where 3 and 6 are in the picture. Are 3 and 6 alternate interior angles? Yeah. You're not allowed to use alternate interior as a reason. Okay? Because it'd be like saying, why, if someone was like arguing with you about like, why are you right about something? And you just kept saying, because I'm right. Why are you right? Well, because I'm right. But you have to prove why you're right, okay? Or why you're the correct person in that situation. I can't just say angle 3 and 6 are congruent because they're alternate interior. I need to prove why that works. Okay, so let's start out with what always goes into first step 1, guys? Given. So on my statement, I'm going to write the given. Angle, or not angle, line L is parallel to line M. I want to prove that 3 and 6 are congruent to each other. But again, I can't go straight there. I can't just use alternate interior angles. It'd be the same thing if someone asked you, like, when we ask our kids questions, you know, and they say, well, because. Well, because isn't a true reason. We have to give another reason why we're saying yes or no. So I want to somehow connect 3 to 6 to each other, but I can't go straight there. So I know that 3 and 6 are congruent. We just know that because of what our background knowledge about alternate interior angles are. So is there another angle in the picture that 3 would also be congruent to that we could make a connection to 6 with? Keegan, what do you think?
7.
So 3 and 7?
Mm-hmm.
Because what kind of angles are 3 and 7?
Corresponding.
Is there another angle that would have maybe worked, Logan? 2, because 3 and 2 are vertical. So I don't really care which one you guys use. You can decide. Okay, because I called on you first, I'm going to go with yours. So I'm going to say 3 and 7 are congruent to each other because they're corresponding. If you had said 2, though, you would say angle 3 is congruent to angle 2, and your reason would be vertical. So because we went from 3 to 7, how do I get 7 to connect to 6?
Vertical.
They're vertical. So I'm going to say down here, angle 7 is congruent to angle 6 because they're vertical. Now I want you to think about this with me for a second. What if I had gone with what Logan had said? If I had said for step 2, 3 and 2 are vertical, how would I connect 2 to 6? They're corresponding. So those reasons that we had there, they're the same, but they would just be in a different order. But we're still seeing those same connections there. Okay, now look at what I have written down for 2 to 3. How can I get from 3 to 6? What'd you say, Parker? Transitive. Okay? Again, think about what we said. 3, let's pretend 3 is Keegan. 7 is Morgan, and 6 is Maddox. Okay? Because they both are common to angle 7, or they're both common to Morgan, we can skip over her. Again, sorry. And we can say that these two are equal to each other, or in this case, congruent. So in this case, we're going to say angle 7 is the same. We can skip over it, and we can say angle 3 is congruent to angle 6 because of what Parker said, transitive. Do we have questions on how that worked? If you guys turn your page over, I'm going to skip over this first one because this first one here is going to be homework for you guys. Okay? So I'm not going to do that one. I'm going to leave it blank, and I want you guys later to go back in and try to do that problem. But there's one more proof that I want us to do today together, which is right underneath that, this one here. This one is giving us still parallel lines. L is parallel to M. They want us to prove that angle 3 and 5 are supplementary. What angle pair are 3 and 5? Same side interior. So you are not allowed to use that as a reason. Okay? We cannot say same side interior at all in our reasons here, because that's not really proving our point. It's just, again, saying, well, because I say so. That doesn't work. Okay? We have to give more justification than just because. So what are we going to start out with? Given. So again, line L is parallel to line M. Okay, 3 and 5 is my ultimate goal. I want to get them connected to be able to say that they're supplementary. Just like on the last one, though, I need to somehow make a connection to 3 to 5. I can't go straight there. So I need to maybe think about, is there another, especially because I see this word supplementary, I'm thinking about what that means. What does supplementary mean? They add up to 180. So is there another angle that 3 is supplementary with? What do you guys think? Is there another angle that 3 could be supplementary with? 1. Is that the only one? Could also be 4. Because what angle pair is happening there with 3 and 1 or 3 and 4? Linear pair. They're making lines. So again, I don't really care which one we use. Let's just go ahead and say angle 3 and 4 equal 180 because it's a linear pair. Okay. Can I connect, because now I'm thinking about them at 4. Can I connect 4 and 5 together?
Yeah.
How?
Alternate interior.
Alternate interior. And so if they're alternate interior angles, what's true about their measurements?
They add up to 90? Or no?
What do 4 and 5 do if they're alternate interior? Are
They
they supplementary or are they the same?
the same.
They're the same. So I'm going to say that angle 4 is congruent to angle 5 because they're alternate interior angles. Okay, so we've kind of made a pathway. We went 3 and 4 together, and now we've got 4 to 5. So we've made our connection. Now, how do we get rid of that 4? So I want you to think about, I can't really use transitive quite yet because they don't look totally the same. We've got up above on number 2, it says 3 plus 4 is 180. And on number 5, it says angle 4 is congruent to angle 5. Yes, they have an angle 4 in there, but we can't just skip over the 180 piece. That's not going to match up with anything on the bottom either. So I want you guys to think about this. If you knew like numbers here, so if you knew how much 3 was and how much 4 was, and if we know that 4 and 5 are the same amount, could we just replace 4 with 5? Yeah. Okay. Striker, I'm going to pick on you. When you play in a game, like in football, what position do you play?
Linebacker.
Okay, if you're a linebacker and let's say you get injured and you have to go sit out, are they going to throw in another quarterback for you? No, they're going to put in what? Another linebacker. Okay? When you're replacing something with something else, you're replacing it with the same position or the same thing, the same amount. So in this case, if 4 and 5 are equal, can I replace 4 with 5? Yeah, because they're both linebackers. Okay, we can just replace them with each other. So I can rewrite this and say that angle 3 plus angle 5 should also equal 180. What property do you guys think that is when we just replace something like that? Substitution. It's the same thing if I'm gone for a day. Who comes in? A substitute teacher does. Okay, so anytime that you're replacing something, like you know they're the same, so I can just swap them out, then we're using substitution there. Okay, so if 3 and 5 add up to 180, that means that they're supplementary, right? And so I can say angle 3 and angle 5 are supplementary. Because that's what supplementary means. So I'm just going to say definition of supplementary. Are we done? Did we get to our proof?
Yep.
Yeah, we did. Now there's an extra blank there, but because you guys were able to get there in 5 steps does not mean you have to fill in something for step 6. So I'm just going to cross out 6. We don't need it. Now, if someone had maybe gone about this in a different way, maybe they would need that 6th blank. So there could be maybe something else that we need in order to fill in number 6, but I'm not going to worry about it. We were able to get it done in 5 steps. Questions on that one? Okay, so down below, there's another problem. This is also going to be homework for you guys. So kind of like what you had yesterday, it's in your packet. You've got 2 problems to do today. And you've got some time left in class. I want you guys to finish. Try to do as much as you can of those 2. And if you didn't finish yesterday's proofs, go back and do the algebraic proofs as well. And if you get stuck, let me know. But they should be really similar to the ones that we did in class today.